Hello dear students. So today we are going to start with refraction. So let's get started already. So in the previous classes we have learnt about reflection. Specifically in the previous class we learnt about spherical mirrors. Today we are going to talk about the next phenomena, which is refraction. So let's see. Okay. So this is the next phenomena that we have to discuss. Okay. Now, what is the situation in which refraction occurs? So suppose this is a medium interface and we have one kind of medium here. For simplicity, we can assume it to be air, and we have another kind of medium here. Again, a typical example would be glass. Okay. Now, different media have got different refractive index. Okay, so let the refractive index of air be represented by mu1. We know that it will be 1. Okay, like refractive index of air is considered to be 1. Okay, but let me just write it in the form of a symbol as mu1. The refractive index of glass is, let's say, mu2. Okay, now just in case if you're wondering what is refractive index, so in any medium, whether it is air, glass, water, or any other transparent medium, the speed of light in the medium, okay, speed of light in the medium is less than the speed of light in vacuum. Okay, the speed of light in vacuum. So if I divide this entire inequation with V, okay, I will get 1 is less than C by V medium, and this ratio is called refractive index of the medium. So refractive index of a medium indicates that the ratio of speed of light in vacuum to the speed of light in that medium. Okay, so that is what the refractive index is. Now for air, the refractive index is considered to be 1, implying that the speed of light in air is almost as good as the speed of light in vacuum, which is true also. You know, the strictly speaking, the speed of light is a little less than C, okay, in air. Okay, but the difference is too small to be considered while doing the calculation, so we don't consider it. Suppose there is a ray of light which is striking this interface at some point, okay, which is striking this point. We call this ray as incident ray. This is something that we have done in reflection also. Now we will draw a normal at the point of incidence. So that normal would look somewhat like this. I hope the line is straight. No, not straight enough. So I'll try again. Now, yeah. Okay. So we call this angle as the angle of incidence. Okay. We call this angle as the angle of incidence. Okay. Now what happens is that in reflection, you know, this ray went here. Okay. That is another story. Okay, here also whatever energy is coming, some part of it will get reflected, but there will be some part which will get transmitted into the next medium. Writing about the energy that gets transmitted into the next medium. So we are going to talk reflected, some part of it gets transmitted. We are going to talk about the energy which gets transmitted. Okay, so when it gets transmitted, what happens is that instead of following its original path, okay, instead of following its original path, the ray bends slightly either towards the normal or away from the normal. Exactly where will it bend, that will be governed by a law. We'll talk about it. But what we will witness is that the ray went somewhat like this. In this particular example, the ray went somewhat like this, and this angle will be called as the angle of refraction. Okay, we denote it by small r. Okay, so I would be called, I hope it is visible. Yeah, this is angle of incidence. Okay, this is angle of incidence. Okay, and R is angle of refraction. Okay, so now if we have to describe what refraction as a phenomena is, okay, so refraction is the process of a light ray bending towards or away from the normal when it changes the medium. Okay, so that process or that phenomena is called refraction. So what is refraction? It is the phenomena of bending of light towards or away from the normal when it changes the medium. That is refraction. Let me write it here. Okay, so if we have to define refraction, what will we write? Okay, refraction is the phenomena of bending of light towards or away from the normal. Okay, it is the phenomenon of bending of light towards or away from the normal when it changes the medium. Okay, all right. So this is the process of refraction. Now, similar to the process of reflection, we have laws that govern the phenomena of refraction. So let me first write those laws. So what are the laws of refraction? Okay, so the first one is that the incident ray, it is very similar to what we write in reflection. The incident ray, the normal, and the refracted ray. Now, what is the refracted ray? I did not point it out. I'll do that. Okay, they are coplanar. That means they all lie in the same plane. Now, what is the refracted ray? So this ray, this ray would be called a refracted ray. Okay, so they all lie in the same plane. So that is the first law. And the second is that mu1 sine I will be same as mu2 sine R. Okay, this equation is called Snell's law. Okay, mu1 sine I is equals to mu2 sine R. So this is called Snell's law. Now, what does this equation tell us? Okay, what does this equation tell us? So if we write sine I by sine R, we get mu2 minus mu1. Now, notice this carefully. Okay, what does this tell us? That if mu2 is greater than mu1, which was the scenario here, the second medium, glass, had a higher refractive index than air. So when mu2 is more than mu1, we can say that this ratio will be more than 1, which also means that sine I will be greater than sine R, or which would mean that I is greater than R. In other words, the ray would have bent towards the normal. See, in this figure, you notice that this entire angle would be called as I, and the angle R that we are getting, it is supposed to be smaller than I, and therefore we can say that the ray bends towards the normal. So we can say that when the refractive index of the second medium is greater than the refractive index of the first medium, then the ray bends towards the normal. Or this can also be said as when ray enters from rarer to denser medium, from rarer to denser. Now keep this in mind, guys. When we talk about rarer and denser in context of light ray, it doesn't mean the mass density. Okay, it means smaller refractive index. It's a comparative word. Okay, so it's a comparative word. So whenever we will be comparing two media, we can call one of them as denser and the other one as rarer. Now the one with the larger refractive index will be called as the denser media. So in other words, between the two, in the denser medium, or the one which larger value of refractive index, light travels slower. Okay, so when light enters from rarer to denser medium, it bends towards the normal, and therefore we can make the other rule also, that when it bends from denser to rarer medium, then it bends away from the normal. If it goes from denser to rarer medium, then it bends away from the normal. Okay, so this is something that you can write. Okay, so what are the conclusions? What are the conclusions from Snell's law? Okay, what are the conclusions? One more conclusion is there, okay, that I did not talk about. This conclusion would be that what if the light enters normally? What if it enters along the normal? In that case, I will become 0, and going by this, if I is 0, then this right hand side should also be 0, which means R should also be 0, which means the ray goes undeviated. So from Snell's law, we can conclude that if a ray strikes medium interface normally, if it strikes medium interface normally, okay, it goes undeviated, like into the second medium, it goes undeviated. Okay, that is first point. Second point, if ray is entering from rarer to denser, I'm writing R to D, from rarer to denser, it bends towards the normal. Okay. And third, if ray is entering from denser to rarer, then it bends away from normal. Okay, then it bends away from normal. So if ray is entering from denser to rarer, then it bends away from the normal. Okay, so let me explain this pictorially also. So let's first talk about R to D. Okay, which basically means that suppose this is a medium boundary. Okay, now guys, listen to this very carefully, very intentfully listen to this. This is something that I'm telling you, this is something which is very important for you to understand. Mathematically it may not be very important, but from the point of getting a feel of the subject or what happens, okay, this is a very important thing that I'm discussing. So my plan is to consider this as rarer medium, this as denser medium. Again, the same example as air and glass. Okay, and we intend to send light rays from different direction and then see that how they will move. So I will start by considering a situation when I've sent a light ray normally. So this ray will go undeviated. Okay, now suppose if I increase the angle of incidence by suppose 10 degree, I increased it by 10 degree. Now I know that it will not go straight, it will bend towards the normal. So I can expect it to move on a path like this. Okay, I can expect it to move on a path like this, or in other words, if you increase this by 10 degree, you can expect an increase of less than 10 degree here. Okay, if you increase the angle of incidence by 10 degree, the angle of refraction will not increase by 10 degree. In this case, it will increase by an angle which is less than 10 degree. Okay, now suppose we further increase the angle of incidence, something like this, we may get a ray like this. Again, it can't go straight, it has to bend towards the normal. So this is the kind of figure that we will get. Now imagine a situation in which we are sending a light ray almost along the interface. Okay, we call this situation as grazing incidence. Okay, so this ray will again go like this. Okay, all right, now you can't send anything else. Like understand this, that this angle is almost 90 degree. Let's say this angle is called the critical angle. Okay, this angle is called the critical angle. Now understand this, if you choose to send ray from other directions, like if you choose to send light ray like this, and then let's say like this, okay, and let's say like this, the corresponding region in which the light will enter into the second medium, okay, that corresponding region would be this, okay, and then it would be this, okay, and then it would be somewhat like this. Now the point that I'm trying to highlight here is that this hemispherical zone from which you are sending the light ray, okay, this hemispherical zone, it maps into a cone. That means it transforms into a cone. You are allowed to send light ray from anywhere, and when it enters into the second region, it confines itself to this cone. In other words, if I am restricting you to send light ray from this point into the second medium, then you can't have any light ray in this region. Any light energy cannot come in this region. Okay, so but it will definitely enter into the second medium. So whenever we are sending light from rarer medium into denser medium, it is bound to enter into the medium. There is no restriction on that, and the hemisphere maps into a cone. Okay, now what if we try the other way around? What do we observe in that case? So suppose now if we are trying from denser to rare, so the light I will be sending from from below. I'm keeping the rarer up and denser below so that we can compare the two figures. Here also rarer was upward and denser was downward. So in this case again, if you start by sending a light ray normally, it will go undeviated. Okay, suppose you thought that maybe I should increase the angle of incidence by some amount. Okay, now you will witness that the ray will not go straight, it will bend away from the normal. So maybe it will bend like this. Okay, you increase the angle further, okay, you increase the angle further, and you will find it going to be like this. And finally, if you make this angle as critical angle, if you make this angle as critical angle, okay, then you will find that this ray is going like this. Are you getting it? Okay, Now suppose you thought that maybe I want to increase this more, I want to send a light ray from here. Okay, now it has no place to go here because this is already, the ray is already grazing the medium, so it will be sent back into the first medium, and now basically reflection will happen, and this reflection will follow the normal laws of reflection also, and this reflection is called total internal reflection. So what is happening is that, again, the cone is mapping uh, into a hemisphere. Okay, the cone is mapping into a hemisphere. The cone is mapping into a hemisphere. Okay, this is critical angle. So again, you see that if you send anything from this cone, okay, it maps into the hemisphere, but if you send something outside this cone, okay, now this is the same region which was prohibited here. Okay, like when you send light ray from here, it couldn't have come into this region. So what if you try to send light ray from this region? Well, it has no place to go into the second medium, so it will get reflected back, and this phenomena is called total internal reflection. Why do we add the word total here? Because the entire energy that will be sent like this will be reflected back without any loss in energy. Okay, so what are the things that we learned here? We talked about critical angle. Okay, we talked about critical angle. So how can we define critical angle? So we can say that it is angle in the denser medium. It is angle in the denser medium corresponding to which the angle in the rarer medium is 90 degree. So angle in the denser medium. So if this is a medium boundary, this is R, this is D. Okay, so irrespective of light is coming from where to where, if the angle in the rarer medium is 90 degree, okay, so like the light may be coming from this and going like this, or it may be coming from this and going like this. The point is that if the angle in the rarer medium is 90 degree and the corresponding angle in the denser medium is critical angle, whatever the angle is, we call that angle as the critical angle. If I now write Snell's law, let's say this is mu r and this is mu d, we will write mu r sine 90 is equals to mu d sine of critical angle, or in other words, you can write sine of critical denser, rarer to denser, it is bound to enter into the second medium. Okay, so the ray must travel from dense to rare for TIR to take place. Okay, and the second condition is that the angle of incidence should become greater than the critical angle. So that would be the second condition that must be met for TIR to take place. Okay, now if I give you a example, okay, so suppose that this is air glass interface, this is air, this is glass, okay, and we have been told that refractive index for glass is 3/2, and we have been told that a ray of light is striking the medium boundary at an angle of 45 degree. Okay, this angle is, let's say, 45 degree. Okay, with a refractive index of mu, this is air with a refractive index of 1, okay, and there is a bulb under the surface of water. Okay, now if you think about all this angle, and now we will be given the depth of the bulb, let us say it is h. We want to know the radius of the disc, this is r. So tan IC, okay, can I say that tan IC will be equal to r by h, or the radius that we seek is h tan IC. Okay, h tan IC. Now if we directly know the critical angle, we can just put it here and we'll get the answer. Suppose critical angle was not given to us, only mu was given to us. You can write tan IC in terms of mu. You know that sine of IC is 1 upon mu. Okay, so if I make a triangle, mark one angle as critical angle, so this becomes 1, this becomes mu. this becomes root of mu square minus 1. So tan IC is how much? Tan IC from here, it becomes 1 divided by root of mu square minus 1, and that's it, guys. This is the radius that we need. All right. So you see that I hope you have understood the process of total internal reflection, and I hope you have got this question also. It's a very common question that is asked. Okay, we'll continue our discussion on refraction in our next class. I hope you enjoyed today's session, guys. And if you did, please hit the like button, share this session, share this video with your friends, and subscribe to the channel if you have not done it.